see where we got to with this. What have you done with the open circuit test values? Got primary power 3.6 watts, which is measured anyway. What have you got for S? Yep. That you can get QM. What'd you get for that? 7.1 var. It's close to what was got in a previous. You ain't going to get the same every time, but that's close enough. And that you got RC. $44.4. That's a good way away from what was. Yeah, but that a small amount make a big difference. Yeah, because I had 400 squared over the 2.6 watts. Yeah, that made that much difference. 44.4 kilo ohms. XM. And lastly, I. Funnily enough, that's really close, and yet that one's 1.6. Okay, so they're the results from the open circuit test, and they look to concur with what was got from a previous year. Sorry? K ohms, yeah. Let's make this one look a little bit more like K ohms as well. Yeah, so there are the results from that. But the short circuit test. We would have calculated a ZP. 160. Close enough. An RP. 116.8 ohms. Looks good. And XP. 113.4 ohms. Yep, all which close enough to what was got before to say they're in the right ballpark. Yep. So then going over to a model now, you can use those values in that model to find the total predicted current and so on. Okay. So have we got results for this? How do we calculate the total predicted primary current? Do I have to do anything else first? Yeah, impedance. ZT. What? Okay. Yeah. I'll do it up here. ZL dash is A squared ZL 1.62 squared times 546 equals yeah. Let's go with. Have you rounded that up or not? Yeah. Okay, we'll round that to 1433. Yeah. So we got RP was 1433. Bring the two resistances together. Because a ZL dash is a resistance, because per resistance. So they come to yeah. Oh, what with various differences? We'll find out. We'll find out, won't we? Yeah. I'll keep writing down what Christians tell me, and then we'll find out how much difference that make, Mike. So that's interesting. How much difference will it make to the polar version? That's ohms, angle 4.19 degrees. How does that compare with what you got, Mike? How does that compare? 5.9? Yeah. So we're talking about 6 ohms in 1500. Do 6 over 1500 times 100%. Not very much. We're probably using a few too many significant figures here, considering that our original measurement were to at best 3 significant figures. Yeah? So really, probably should only be using 3, but no worries, we'll carry on. Alright? Therefore, current this 1553.8 angle 4.19 equals amps angle yeah. By the time you get to the end and you round it to a sensible value, it's not making a great deal of difference. Alright, so that's what you're expecting the primary current to be. Is that one of the things we got recorded on here? Yes. What's that, 250 milliamps, isn't it? Yeah. So put that in there, 250 milliamps. Is that what you got, Sophie, James? Okay, that's on, stop you. Confused as what you got to do?
Yeah.
Yeah?
Well, I can't quite remember last week. But
Yeah, you'd put the parameters from the open and closed circuit tests that you calculate into that model, and then use the model to.
what we did last week.
Yeah. So we done an example, didn't we?
Yeah.
We took some measurements last week. So you need, yeah, that's what we went through, is using them. So make sure you understand, using those measurements we made last week. And I didn't go through in detail, but if you look at the example we done before this, there are calculations to calculate what S, Q, M, RC, and XM and I are.
Yeah, I managed to do the open circuit.
Yeah, and then the closed circuit, use these values to find the impedance RP and XP, and then use that data in the simplified model to determine the values that we're going to compare with the measurements on there.
Okay.
All right?
It'll work now all the way.
Yeah. Yeah. All right. Because ultimately, that's what we're going to compare, is that those 4 things in calculated value compared to what we actually measure on the rig. Trying to prove that this model is a valid model for that to use for a transformer like that. Yeah? Alright?
We use the values this one.
The open circuit will give you the power loss, heating in the core, and the flux losses. Yeah? Alright? Sorry, the magnetizing current. But if you remember, when we simplified the model, we said that that current is, once that's on load, significant amount of load, that current that does the core heating and magnetize the core is negligible compared to the current flowing to service the load. Hence, you can ignore it. So we went through all that thing of making that big transformer model, didn't we? And then we simplified it. And now we're going through a process of saying, does that simplification work for this transformer? Alright? So yes, we've done a closed circuit test, but ultimately, the only parameter we're using from that to do the on-load model under there is A, because we're using the simplified model. Alright? Yeah? So, we've found the current, 250 milliamps. Secondary current under load. How do we find that? Yep. Because IP is equal to I2 dash. So if we then multiply it by A, we transfer it back to the secondary. Yeah. So that's 1.62 times 0.25 angle minus 4.19 for completeness equals 0.41 amps, angle the same, 4.19 degrees. Yeah. So there's a second thing that we can put in our table for comparison. There's 410 milliamps secondary current as predicted. Secondary voltage. We want to find E2. How do we go about doing that? E2 dash is equal to I2 dash, which is equal to IP. Yeah, so we can say, we can just call that IP times the ZL dash. Yeah, because that's our load. Yeah, which is 0.25 angle minus 4.19 times 1433 ohms. Following? Yeah? $358.3 volts. Yeah, angle minus 4.19 degrees. So that gives you an indication of how much of the 400 volts is being dropped across the other two components. Yeah, because the load reflected to the primary side is 42 volts, nearly less than what has actually been input at the outset. Yeah. And then how do, so then we get, so yeah, E2 is equal to E2 dash over A. That's 358.3 angle minus 4.19 degrees divided by 1.62, wouldn't it? Comes out as and the angle's the same. Right? Yeah. Follow James, yeah. So that's 221.2 volts we can put in here as secondary voltage. Power output. Yeah. So we can say power out as ZL ignoring angles because they're in phase with each other anyway. There's a per resistance P2 is equal to I2 E2, the magnitudes of, yeah, which are 0.41 and 220 something. Not 0.41 times 221.2 equals 90.7 watts. So that's the last entry in our comparison table, 90.7 watts power output. So that's what the model predicts. So the process was do open and short circuit tests, use those results to work out the model parameters for the simplified model, place them in the model, calculate the values. Now we'll just pop over and have a look and see what we get in comparison on the real transformer. So for the sake of math, we'll just put those values in here. What was the primary current, Christian? 276 milliamps. Secondary current. Secondary voltage. And 97 watts. Yeah, so fairly close prediction from that model of what that transformer is going to do. Yeah. But you've hopefully found it useful to actually apply it to a practical circuit and take some measurements and see that that does actually mimic what a transformer would do. Alright, so that's that, and that's essentially that's the teaching finished for the module now. We go into full-blown examination revision mode now. Yeah, so I'm going to give you some stuff to have a go at. If you're struggling, please ask and I'll help. If everyone's struggling, we'll do something on the board and so on, and that will anything relevant will be bunged on there for reference. Right?